All right, so let me remind you where we were yesterday. So we were looking at the random cluster model, and we were interested to get bounds on the critical points compared to the self-dual points. So what I showed you yesterday was Zhang's argument saying that the self-dual point was not supercritical. So what we have for now is the inequality that P self-dual is below the critical point. And now what we want to show is that as soon as you look slightly above the self-dual points, then you are in the supercritical regime. And that will give us the other inequality. So the goal, I showed you the plan of the proof, and the plan is first give bounds on what happens at the self-dual point, saying that already something macroscopic happens, and then give a sharp threshold to say that what happens when you increase P a little bit is enough to show that you are supercritical. So the second step is what Hugo will do tomorrow, and today I will do the Rousseau-Simon-Welch theory applied to the random cluster model. So the main result that I will prove today is this. And I will state it a little bit informally, and you will see why in a minute. So look at the random cluster model for P equal to the self-dual point and Q larger than 1. And look at a large box. So the large box will be of size an times n. And you want to know with which probability there is some connected path inside the box crossing from the left to the right. So this means that this path is formed of open bonds in the model. And you want to know at the self-dual point, and I'm not putting Q here, but Q is fixed and Q is bigger than 1. You want to estimate this probability and give a bound that does not depend on n. And that will tell you that you will see big clusters without looking too far away from the origin. So the goal is to show that this probability is bounded below by some constant which depends only on A and Q, but not on n. So constant depending on A and Q. So if we have this, we have a lower bound on something that happens at the self-dual point, and then maybe if you increase P a little bit, since the box is very large, if you increase P a little bit, it will make this bound very close to 1, and that will be enough to show that it becomes supercritical. So this is the goal, and unfortunately stated like that, it's not always true because I'm still having to put something about the boundary condition. And in fact, if you put the free boundary condition, and this is not expected to hold at least for large Q. So for now, let me state it with wired boundary condition, so with one boundary condition. And in fact, we'll prove this, and we'll prove this also for periodic boundary conditions. And we will need the periodic boundary condition in a crucial way because we want to apply a sharp threshold, and for that it's nice to have transition invariance in the model. And so we'll see exactly how it goes. So this is the statement, and I have about an hour to show you why this is true and why the self-duality tells you something about what happens. So just to warm up, what happens at Q equal to 1? It's always informative to look at the case of percolation because there is no problem with the boundary condition, there is lots of independence, and everything works fine. So Q equal to 1, and I will look at crossing events like that. And the crucial argument is the following. We want to use self-duality, meaning that we will use duality somewhere. And the key estimate is this. Take a square box. So a box which is of size n by n. So somewhere behind there is Z2, and you look at percolation at the self-dual point. So P is equal to 1/2 in the case of percolation. And you want to look at the events that there is a horizontal crossing here in the square. Okay, let P be the probability that this occurs. Okay, so pi is the probability that the square is crossed. What is the complement of this event? It's the event that the square is not crossed. But by the duality argument that I introduced yesterday, if the square is not crossed, that's because the cluster of the left bond is surrounded by a closed family of bonds. And this is exactly the same as saying that there is a dual path crossing vertically in the square, blocking the horizontal crossing. So if there is no crossing here, if something blocks the crossing horizontally, the only thing that can block is a vertical dual crossing. Okay, but if you look at the dual model, it's the model with parameter 1 minus p, and 1 minus p is still 1/2. That's because we are at the self-dual point. So the dual model is exactly percolation at the same point in a domain which is a square, and you want to cross vertically. But crossing a square horizontally or vertically is the same. So what you get is that 1 minus pi, so the probability of the complement event, that's the probability of a vertical dual crossing, and this is equal to pi, because it's the same event. It's crossing a square with percolation at the point p equal to 1/2. And so from that, you get that the probability that you cross a square horizontally is equal to 1/2. So this is for percolation at p equal to 1/2 and q equal to 1. And here I don't have to care about boundary conditions because it's percolation, so it doesn't depend on boundary conditions. So that tells me that in the case of percolation, I get a bound for the C of A and Q, which is C of 1 and 1 is equal to 1/2. So this is an a priori bound which is very easy to get. And now we need to do two things. So the first is to generalize this bond to the case where Q is larger than 1. So generalize to Q strictly larger than 1. And the second thing is to generalize also to shapes which are not squares. So rectangles. And that will be C larger than 1. A larger than 1. And as it turns out, these two steps are both tricky. And the first one is tricky because of boundary conditions, because you need to keep track of what happens when you do duality, and the dual event is not speaking about exactly the same measure, so you need to be more careful than that. And the second, well, it's already tricky in the case of percolation because you need to build something long out of something which is not long. So you will see how it goes. And essentially, you still need to keep track of boundary conditions, and, well, you need to plug things together. But somehow the more important one is this one, because that's where the physics goes. And this is where the trick goes, but, well, we'll see what happens. So how to do what? So remember that what I told you yesterday was that if you look at the dual model, what you get is a random cluster model, but if you keep track of the boundary conditions, you have to change the boundary condition when you look at duality. So what we need to show is that crossing with wired boundary condition is very likely. So okay, let's look at pi q, which is the probability at the self-dual point with wired boundary condition that you cross a square. And let's try to do the same thing as before. We want to use duality to estimate this crossing probability. So what do? We look at the complement event, so 1 minus PQ. That's the probability that there is a dual crossing vertically. And the dual model is the model at the self-dual points, but with free boundary condition. So it's P0 P self-dual Q of crossing a square. So if we knew in advance that P0 and P1 are the same measure, then we would get a bound which is the same. We would get 1/2. But we don't, and I told you that actually we don't expect the theorem here to be true for free boundary conditions. We expect that this would go to 0 if you put free boundary conditions. So all you get from what we have for now is that this is at most equal to P1 just by monotonicity of the same thing. And this is pi. Okay, so what we get from this is some bound, which is actually not too bad, but which will be very difficult to generalize, and which, well, actually what you get is that this is larger than 1/2 and this is smaller than 1/2. So for wired boundary condition, we have this. But it's not enough to have wired boundary condition, and you will see exactly why tomorrow. So we need to refine this estimate to have something a little bit more self-dual, just to make things easier for later. So specifically, what I will prove is not this, but is this for periodic boundary condition. And for periodic boundary condition, we'll have a little bit of trouble to have the right estimate. Okay. So I will look at periodic boundary conditions, and I want to apply the same argument for periodic boundary conditions. So remember, this is the box of size. So I will look in a finite domain. I will look at a box of size m. So n is fixed, n is the size of the box I want to cross, and I want to put this box in a domain for which I define the model. So what I want is that m is larger than alpha n, than an. So I want the box to fit in the domain where I define the model. And the boundary condition I take is, well, Hugo did this picture yesterday, or on Monday already. What I do is I take a collection of bonds connecting pairs of vertices across the square. So that's the same as defining the model on a torus. And this gives me a periodic boundary condition, which I want to call Pm. So P for periodic and M for the size of the Pm. M for the size of the domain and P for periodic. And I will look at this, P self-dual and Q. So this is really the measure I want to look at. So what do I want to do? I want to estimate first for Q equal to 1, for A equal to 1, the probability to cross a square. So I want to apply the same construction. I want to look at pi, which is the probability to cross a square, and I want to look at the dual event. And the dual event is still the vertical crossing by a dual cluster. What I don't have for now is the description of the dual model as a random cluster model. And that's a problem. So the problem is the dual model is not a random cluster model. For those of you who did the exercise of actually proving that the dual model of the free boundary condition is the wired boundary condition, if you want to apply Euler's formula, somewhere you have to use planarity. If you want to really construct a dual of a graph, you need the graph to be planar. And the graph we have here, including the bonds here, if you want to apply duality, is not a planar graph. It has genus 1. And so if you look at the dual graph, the counting of the clusters will be a little bit off. So it's not exactly a random cluster model, but it's almost a random cluster model. So what you can show is that the random Nicodemus derivative of periodic self-dual star over the initial measure. So if you compare the dual measure to the initial measure, you don't get exactly 1, but this is bounded above and below. So this is order 1. And in fact, what you need to take into account is whether there is a cluster going around, where you need to see if you have a cluster which is not contractible. And this changes the counting, but there are only a few cases that you need to take care of. So we have a constant here, and this constant is of order, it depends on Q. So the constant here depends only on Q. Yes, that's what I mean. You need only on Q. It doesn't depend on the size of the domain. It only depends on Q. It's just an off by 1 counting of the clusters, so it can only occur once macroscopically. But if Q is fixed, this is fixed. Okay. So what we get from this is that now we can apply the same argument as before. We can do this. We introduce pi q, which is the crossing probability of a square with periodic boundary condition. So periodic m at the self-dual point of crossing a square. You look at duality. The probability of the dual event is equal to this up to constants which are uniform in Q. So you do the same argument as for percolation, and what you get is that pi q is, so what you get is something like eta 1 minus eta, where eta is positive and depends only on Q. And it's something like 1 over 1 plus Q squared or something like that. So what you get is this. So this is still the same as, more or less the same as for percolation. The general idea is you use duality to give a comparison between the probability of an event and the probability of its complement. And if these two have the same order, then you cannot be close to 0 or 1, and it gives you a lower bound. So that's the first step. We will want to glue things together, and just let me make one picture to tell you where the problem will be, and then I will come back to a priori estimates. So this was part of one, but just to motivate what I will do next, let's look at a large rectangle, which is not a square. So I will put it in yellow because it's kind of out of the flow of the proof, but it's more like motivation. So this is a rectangle, and say I put the picture for a equal to 3/2 here. So it's not a square, it's strictly longer than a square, and you want to know if you cross it horizontally with a significant probability. Well, because it's longer than a square, it's more difficult to cross it. So maybe you can't cross squares, but you cannot cross rectangles. So you need to actually show something. Okay, what can we do? We know how to cross squares. So maybe we cross this square, and this square is crossed with positive probability. Okay, maybe we cross the second square horizontally. This still occurs with positive probability. And these events, they are increasing events. They are existence of open bonds. So if you open more bonds, you still cross the same square. So by the FKG inequality, all these events are positively correlated. So the probability that these two events occur simultaneously, it's positive. It's bounded below by C of 1 squared. C of 1 is crossing probability for a square. But this is not building a crossing of the rectangle. You need to connect these two crossings somehow. Okay, how do you do that? Well, you make a vertical crossing somewhere. So where do you put it? If you put it in the left square, well, it might pass to the left of this path, so it doesn't work. If you put it on the right square, it might pass to the right of this guy, so it doesn't work. And if you put somehow a square in the middle, well, you can cross vertically, and the vertical crossing might look like this. And it still doesn't work. So you can build arbitrarily many paths, and if they only cross squares, you will never make a crossing of a rectangle. So you need to be a little bit clever at these points to be able to connect things together. And already for the case of percolation, this is not a trivial question, going from a square to a rectangle. So we will need to have some tool that connects crossings of squares together to make something a little bit larger. So we need a new tool. For now, we know how to cross squares by duality with periodic boundary conditions. But we need to cross some things that are not squares, so we need a new tool. So here's a lemma. Which is somehow the key to be able to connect paths together. And it's about symmetric domains. So forget for a second that we are looking at the periodic boundary conditions or free boundary conditions. What I will show is something at the scale of the domain in which the model is defined. So I will look at the symmetric domain. So lambda will be the box in which the domain is defined. And I'm assuming that lambda is symmetric. So lambda will look like something like that. And I'm assuming that there is an axis of symmetry here. You need to convince yourself that this is symmetric. It looks symmetric from here, but not from the front. Okay, and I pick one point here, and it's symmetric here. Maybe I should put the rectangle. It's easier to make it symmetric, but it looks less generic. So this is the domain, and it's symmetric. Okay, and I will put boundary conditions on the domain, which are wired here. So this is 1, and this is 1. And I want to estimate the probability that I cross between this part of the boundary and that part of the boundary. And what I will show is that this is actually bounded below by something like 1 over 1 plus q squared. And maybe there's a half, maybe there's a q, something like that. Some constant which depends only on q, but not on the size of the domain and not on the shape of the domain, except for the fact that the domain has to be symmetric. So this is a little bit stronger than crossing a square because it will allow me to cross domains of any shape, provided that I manage to put the correct boundary conditions on the boundary of the domain. Okay, here I have to do things properly. But maybe you can already guess what the proof will use. Because essentially we only have one tool. We only have duality. So the proof, have to use duality. So if pi is the probability of this guy, I want to look at the complement of this event. So that's the existence of a dual crossing. So if pi is the probability that in this domain here I cross like this, and this is the wired part of the boundary, then 1 minus pi. So here I don't put the boundary conditions because they are part of the picture. This is the domain in which the model is defined. There is no ambient space. This is the graph. But we are at the self-dual point. 1 minus pi is the probability that there is no crossing here. So it's the probability at the self-dual point in this domain with wired here and wired here that there is a dual crossing like this, which blocks the initial crossing. So I have to look at the dual model and say that this is, so P star again, P star is the distribution of the dual model. And for the dual model, I need a crossing like this. So I need to tell you what the dual model is. So for that, well, you have to remember the argument that gave us the statement of the duality in the first place for free boundary conditions. The argument was this: if you have a domain with free boundary conditions, and if you look at the dual graph, well, the dual graph looked something like this in yellow. There was one piece of the lattice inside, and there was one huge vertex on the outside, which in fact I replaced by a whole layer of vertices around the square, but all wired together deterministically, so with wired boundary condition. And that's why the dual of the free boundary condition was the wired boundary condition. Here what I have is something like that. I have a domain, and I have two wired parts on the boundary. So this is wired, and this is wired, and the rest is not wired. So this is the domain inside. Inside it's a regular grid, and outside I have these two wired arcs here. So what I can do is look at the dual graph and see what happens. And maybe it's a little bit simpler to imagine that these wired arcs here, actually they come from the same kind of constructions. So there are two vertices, two big vertices connected like that. This is the same as putting a wired boundary condition. It's adding one vertex and connecting it to every vertex on the boundary. So this is my graph, and now I look at the dual graph. So the dual graph has one piece which is like a lattice inside. Okay, this lattice goes also inside these triangular faces here. So it goes like that, and like that. And there is one outer face in the white graph, so there is one outer yellow vertex which is connected to all the vertices on the boundary. So to the top here and to the bottom. And also here. But the boundary is only on the top and the bottom because, well, this is not a neighbor of the outer face because it's separated by many bonds. So somehow the yellow boundary is only living at the top and at the bottom. Okay, and now if I look at how to replace it by a layer on the boundary, well, the yellow graph I have is a rectangular piece of Z2. And then there is a huge vertex which is connected to the top and to the bottom. So what I can do is I replace it by one layer here, which is wired, one layer here, which is wired. And there is one thing in addition, these two wired arcs, they still are part of the same boundary condition, so they have to be wired together. So there is one additional bond here. So in other words, if you look at the dual of this boundary condition, so wired here, and free here, well, maybe I'll do a picture. So the dual boundary condition so if you look at this boundary condition, which is the one we're interested in, then the dual of this, what is it? It's a domain with the same shape. So it's the same shape here. We get wired boundary conditions here and here, which corresponded to the free parts of the initial boundary condition. So it's wired here and here. And these two, they are connected to each other. Yes, it's not symmetric. It's symmetrized enough. It's the same because it's a symmetric domain, but right, it's swapped, so it's wired here, it's wired here, and it's connected on the outside. So this is the dual boundary condition. So what you have is that the dual model of the random cluster model in this is a random cluster model with the same parameter p, but on this graph with this boundary condition. So what you have to have is that the probability that you cross like that plus the probability that you cross like that is equal to 1. That's the same duality argument. You look at an event, you look at the complement, you write it as a dual model. And what you have is that the sum is equal to 1. So what you get is almost what we want already. It's already almost a bound on this. Because this event, if you make a symmetry, it's almost the same as this event. The only thing that changes is that there is this additional bond here on the outside connecting two boundary components. So the last step would be to control what happens if you add one bond like that on the boundary. And the fact is this. So I will compare what happens if I add this bond. So if I take any configuration omega inside the box, and I look at the probability of omega, so let's call, yeah, maybe in the picture is better. I take this domain, The fact is much more generic than this particular setup here. I want the probability of omega inside the domain with some boundary condition containing this bond. And I want to compare that to the probability of the same configuration inside, but without this edge as part of the boundary condition. So in other words, if you write boundary conditions as a collection of bonds between the sites on the boundary, you need to control what happens if you remove one of these bonds. So what happens? Well, this probability, maybe it's better if I switch here. This probability, you need to come back to the definition of the model. And I really want to go into the details here because it really tells you something about the physics here. It tells you why this modification is small. So remember, P of omega is what? It's 1 over z times P to the number of open bonds, Q to the number of connected components. So what changes from one boundary condition to the other? You remove one bond. But this bond is outside, so it's a virtual bond. It's not part of omega. So this is not changed. So this is not changed. This might be changed. It might be changed in this situation that omega has one component here, one component here, that were connected from the outside by this virtual bond. Because now, with the virtual bond, this counts as one connected component, and if you remove it, these two are not connected anymore. And so you gain one boundary, you gain one connected component. So maybe if you remove this bond, you increase k by 1. But that's all that can happen. So this maybe you go from k to k plus 1 by removing a bond on a boundary. So maybe you add a factor q here. And on the other hand, you need to take care of z. Z is the normalizing factor. So z is the sum for all omega of this term here to make it a probability measure, q to the k of omega. So for some of these terms, you will multiply by q, and some others you will not do anything. So z has to increase a little bit, but not more than a factor q. So this part here is between its original value and multiplied by q, z as well. So what you get is something like this and this. They differ at most by a factor of q squared. So the ratio between the two is somewhere between 1 over q squared and q squared. I'm not being optimal at all. I mean, one of these bonds is trivial because by monotonicity, this is larger than this. So what you have is that this has to be bigger than 1. So in fact, what you get is between 1 and q squared. But here I did not use monotonicity. I just used this formula. And if you don't have monotonicity, well, you can still control the ratio between 1 over q squared and q squared. So if you step back a little bit, what you get is that this crossing probability is equal to this crossing probability up to a factor which is fixed, which is of order q squared, but q is fixed. And so what you get is exactly the lemma that I announced, that this crossing probability in a symmetric domain is of order 1 uniformly in the shape of the domain and in the size of the domain. Only q occurs in the bound that you get. All right, so how do you use that to trick the model into crossing a long rectangle? So I'm going to draw a picture that we drew maybe 100 times before we got it right. And in the end, it doesn't look so special, but we'll see. Maybe I need one more lemma. So remember, I want to cross a long rectangle. I know how to cross a square. There is one thing a little bit more difficult than crossing a square that I can get for free. It's this. Take a square, and you want to cross it horizontally, but only from 1/2 of the boundary to the other side. So you want to do this. Say with periodic boundary condition in a larger domain. So how do you do that? Any guess? Okay, let's call that P1. And let's call P2, so this is P1. Let's call P2 the probability that you cross from the lower half to the right one. So this is P2, probability that you cross from this half to this. So of course P1 and P2, they are the same event up to a reflection. So P1 is equal to P2. But if you look at the union of these two events, well, it's exactly the crossing between the left and the right. If you cross from the left to the right, well, either you cross to the top or to the bottom. But if you cross to neither, you don't cross horizontally. So you have a union of two increasing events of the same probability, and you know that the union has a probability which is bounded below by something of order 1. So what you do is the square root trick that I did yesterday, and this tells you that P1 is bigger than something like 1 minus this constant to the 1/2, where this is the bound that we get for crossing a square. So this is still strictly positive, and it's still uniform in the size of the domain. So by the square root trick, you get something a little bit more difficult. You can localize the landing half of a crossing, at least on one end, to 1/2 of the square.
Why P1 is equal to P2? Everything is inside the large m by m square, and the situation is...
Yeah, assume it's in a periodic boundary condition. So if you reflect, you don't change the domain. You are not living in a large domain of some shape. You are living in a torus with periodic boundary condition.
It's in the center of the torus.
But there's no center of the torus. It's invariant by translation. So you put it anywhere in the torus, but if you reflect, you get the same model. So P1 is equal to P2. If you prefer, you can put an arbitrary domain, but then it has to be symmetric. So the advantage of having periodic boundary conditions is that you have some symmetry in addition to the well, you have enough symmetry to get something like that. Okay, so this is also bounded below by some positive constant which is uniform. So maybe I keep this on the board and I make the picture here. So what I gain from this is that I have some control on where the path crossing the squares that I did 20 minutes ago, where they land. But I still want to cross a rectangle. So this is a rectangle, and it's still a rectangle of size 3/2. So this is A. Now we'll still look at two squares, one here, so this is N, this is N, and the other square which is here, and this is N. So I want to build a crossing inside this big rectangle from crossings of squares, and what I'm allowed to do is to cross squares from half of the size to the opposite side, and I'm allowed to use FKG to make the intersection of different increasing events. So, okay, first, I want the first crossing to cross the first square horizontally, and I want it to land on the top half here. Okay, this has positive probability. And then the second square, the vertical square here, so this is between this and this. And the second square, I want to cross it vertically from the top to the left half here. Let's see if I get this right. So from the left half here to the top. Okay, so this is the blue crossing. And I don't want to draw the blue crossing all the way. And then somewhere I will put a horizontal crossing, an arbitrary horizontal crossing of this square, which will be in orange. It's not, doesn't look different enough. Okay, so I will have 3 crossings. So 1 in yellow, 2 in blue, and 3 in purple. And out of these, I want to make a crossing of the rectangle. So if you look just by topology, the path number 2 has to intersect the path number 3, because they cross the same box in opposite direction. So gamma 2 intersection gamma 3 is not empty. They have to cross at some point. So if I know that gamma 1 and gamma 2 intersect, if I know in advance that this blue path will intersect the yellow path, then I'm done. Because then I can go from the yellow to the blue, from the blue to the purple, and it builds a horizontal crossing of the rectangle for me. So if they intersect, then I'm okay. What if they don't? If they don't, it's because the blue path does something like that.
Why don't you change the order of the path and the, I mean, in the vertical crossing?
Yes? Well, you cannot change really. If you cross from this to this, oh, you can still go there. This is not open bounds. It's just a notation that you need to land here. But the path gamma 1 is just this squiggly part. So you can still avoid it. It's a very symmetric picture. Yeah?
In fact, if you take one like that and another like that, and the third like that, it will do this.
No, well, it will make the same picture as before.
No.
You cannot ask for 2 symmetric paths to be present.
Why?
Because it's still disordered inside.
The probability of the path like 1 is positive.
Yes?
The probability of the path coming from the right
Here?
side. No, from the right.
Yes?
To the top half.
Yes?
Is positive.
Yes? So it crosses like this.
Yes. And you have a square in the top. You have a
Yep.
small square n over 2 times n over 2.
Yes?
That you cross vertically with positive probability.
Yeah, but it will cross here, but there's still room here. You don't know exactly where you cross.
You have 3 crossings and they're positively correlated.
Yep. But you need to connect to the other one. You don't know that this and this are connected.
Yeah, sorry.
Now you really need something. Well, you're close to what you have to do, but you still need to do something. So assume that gamma 1 and gamma 2 do not intersect, that you are in this situation here. So from the lemma, you know from the previous lemma about symmetric domains, you kind of know where I'm going. You want to build somewhere a symmetric domain with correct boundary conditions and show that this is crossed. So where is the symmetric domain? Well, I will do the symmetric of this path here, and the symmetric of the blue path here, like that, and define this as the symmetric domain. So this is my symmetric domain. For now, it's just a definition of a domain in the box, and I did nothing with the bounds or anything. I just drew the box here. So this is a symmetric domain. So I know that in some cases I can cross symmetric domains. I can cross them if I look at a random cluster model inside with the correct boundary conditions. So what do I do? Maybe I should be a little bit, still have 10 minutes. So, yeah.
Okay.
So now I will have to do this properly. So you need to define this domain in such a way that you can apply the lemma about crossing symmetric domains. So you need to specify exactly which path you are looking for, because for now there might be many horizontal crossings like that. And you have to pick one if you want to be a little bit explicit. So more explicitly, gamma 1 will be the topmost crossing, satisfying this, so landing in the right spot. So it's the topmost in the sense that there is no horizontal crossing going something like that. So what does it say? It says that gamma 1 is open, but any path going above gamma 1 has to be closed at some point. So it tells me something about the state above gamma 1. It tells me negative information about what's above gamma 1. Many bounds have to be closed for this to be the topmost crossing. It tells you that there is no crossing higher than that. So this is negative information above gamma 1, but it tells you no information about what's below gamma 1. For it to be the topmost crossing, you can change anything below gamma 1 and it will still remain the topmost, because you cannot make it move higher by changing something that's below. So by restricting to the topmost crossing, you get negative information here. I put it here. And for gamma 2, I will take the rightmost crossing. So gamma 2 will give me negative information about what's on its right. So negative information here. But nothing inside, nothing on the left of gamma 2. Okay, so now if I condition on gamma 1 and gamma 2, and I look at what happens inside this domain. I condition on gamma 1 and gamma 2, and I also condition, then once I know gamma 1 and gamma 2, I condition on all the parts that is in green. I condition on all that is outside this domain, all that is not hashed in white. And I look inside this domain omega here. So remember, we have the domain Markov property. If I condition the random cluster model on what happens outside omega, what I see inside is a random cluster model with some boundary condition. And what can I say about this boundary condition? Well, these bounds are open, these bounds are open, and here there is something which I don't control. So given gamma 1 and gamma 2, so given gamma 1 and gamma 2, the probability that in omega, which is this domain here, I cross like that, in omega, this is the probability for a random cluster model with some boundary condition. And by monotonicity, this is larger than the probability in the domain of the same shape, symmetric, like this, that I cross for any other boundary condition which is smaller than the one I get from the conditioning. So what I get from the conditioning is these pieces of gamma 1 and gamma 2, they are open, so they are wired here. So this is wired on gamma 1, it's wired on gamma 2, and here I get some information. It's bigger than nothing. It's better than nothing. So I get a lower bound if I put nothing here. If I put 3 boundary conditions. This is worse. It's more difficult to cross. But now this is a symmetric domain. So this is bounded below by some constant depending only on Q. This is by the lemma about symmetric domains. Yep?
Why is it symmetric?
Oh, it's symmetric because you build it by looking at the symmetrized version of gamma 1 and the symmetrized version of gamma 2. So it's symmetric across the vertical line. That's how you define omega by taking gamma 1 and it's symmetric and gamma 2 and it's symmetric. Then you take the intersection. So you define it like that and it's symmetric. Okay, so now if you put everything together, what you get is that the crossing probability for this large rectangle is larger than the crossing probability for a square cubed times this C of Q for symmetric domains. And so what you get is that C of 3/2 and Q is strictly positive. So that was a lot of work to cross something which is not much bigger than a square. It's still a fixed shape. But using FKG and using a little bit of a control on boundary conditions on some domain, what we got was a lower bound on crossing probability for this domain. And remember, this is still for periodic boundary condition because what we need in advance is crossing probabilities for the square. So what we get is this for periodic boundary conditions. So now the rest is very easy. I know how to cross a rectangle which is strictly wider than a square. What if I have to cross a very long rectangle? So A much bigger than 1. I went all the way to A equal to 3/2, but maybe I will have to cross longer rectangles. So this is a long rectangle. How do I cross it? Well, now it's very easy because I can put horizontal pieces of size 3/2 n by n. So this is n and this is an. I can put rectangles of size 3/2 of n so that they overlap on squares. So there will be one like this, and then there will be one like this, and then there will be one starting here, etc. The number of rectangles I need is something of order A, or twice A. Each of these I can cross horizontally with a positive probability. Like this, and maybe this one, and then this one, etc. And by FKG, the intersection of this still has positive probability. The bound will depend on A, because it depends on the number of events that you need, but it does not depend on n, because the bound is the same for every n. And now I have vertical crossings of squares for free. And if I cross this square vertically, now it has to intersect this path and that path, so it has to connect these two paths together. And now if I cross each of the squares like that vertically, each vertical crossing will connect one of the yellow crossings to the next one. Because the overlap now is a square, so I can cross the overlap itself. So the union of all these paths has to contain a crossing of the big rectangle. And so what you get is that by the FKG inequality, the lower bound on crossings of rectangles of shape A, well, this is bigger than something like the lower bound for squares, for rectangles here of size 3/2, to the power the number of something like that you need, which is of order A. So it's still strictly positive. Of course, the bound cannot be uniform in A, because crossing a very long rectangle is very difficult. But it does not depend on n, and that's what will count here. So that's the end of the proof for the Russo-Seymour-Welch version for the lower bound. So let me restate it. So here is the proposition. So for every A bigger than 1, there exists C of A and Q, such that for every n large enough, the probability with periodic boundary condition in a large enough box that the rectangle will fit in it at the self-dual point that you cross horizontally between an and n, this is bigger than C of A and Q. So this is what we have. There is this lower bound with periodic boundary condition. And hence, if you want it for wired boundary condition, you just compare the boundary conditions, and wired is bigger, so you also get this bound for wired boundary condition. But the periodic will be needed tomorrow, so you need this. And there is no simple proof if you want to do it for wired. So this is what we get. So tomorrow you will see, no, it's on Friday, you will see how to go from this, increase P a little bit, and obtain a bound which is close enough to 1 that you can show that it's supercritical. So I think I should stop here.